dear students, welcome to Easy BTech, your guide for BTech and beyond. Today we are going to discuss topic transfer function of the system and distortionless transmission of a signal. So these two we are going to cover. So before going to our topics, all of you subscribe, share the channel. It is very useful to you. So all of you please do that. Let's start our session. Today's topic, transfer function of linear system. Linear system transfer function. Transfer function of linear system. So linear system we know. So I am plotting linear system. This is the linear system. So here input signal is x of t. This is the input signal, and the impulse response of the linear system h of t, and output signal y of t. So the expression for output y of t. So what is the expression of a output signal for linear system in case of linear system? This is a linear system. What is the expression? Y of t equal to x of t convolution h of t. So here x of t is the input signal. What is x of t? It is input signal. And what is h of t? Impulse response of the system. Impulse response of the system. Impulse response of the system. Response of the system. So by doing convolution of these two, we get the output of the linear system. So this is in time domain. This output is in time domain. So in frequency domain, so we are going to apply Fourier transform on output y of t in frequency domain. So apply Fourier transform. Then Fourier transform of y of t is equal to Fourier transform of x of t convolution h of t. So if you see right side, convolution, here convolution in time domain. In Fourier transform we have property convolution in time domain will become multiplication in frequency domain, right or not? So convolution will become multiplication in frequency domain. Convolution in time domain is equal to multiplication in frequency domain. This will become multiplication in frequency domain. So as per this, we are writing y of t is y of omega, and x of t convolution h of t and Fourier transform. It will become multiplication in frequency domain, that is x of omega h of omega. So now the transfer function h of omega, that means output y of omega by x of omega. So what is y of omega? What actually y of omega? Fourier transform of output, right or not? Divided by what is x of omega? Fourier transform of input. So this ratio is called transfer function of the system, h of omega. So here h of omega is called transfer function of the system. Transfer function of the system. Transfer function of the system. right? So simple definition, transfer function h of omega equal Fourier transform of output by Fourier transform of input. So generally this h of omega is the complex quantity. In most of the cases this h of omega is complex quantity. That means it has real part and imaginary part. It is a complex quantity. So this h of omega we can express like magnitude and e power j theta or e power angle of h of omega. Here theta is the h of omega, angle of h of omega. So here this represents magnitude, this represents magnitude, and angle h of omega represents phase. This is the phase. Okay. So this is the magnitude and angle h of omega is the phase. So h of omega is the complex quantity. We can write like magnitude e power j theta. Okay. So now magnitude plot, phase plot. So that also we can discuss now. So magnitude plot means magnitude versus frequency. Phase plot means phase versus frequency, right? So magnitude plot and phase plot. So these two are called frequency response. The two plots, magnitude plot and phase plot, is called as frequency response. Okay, magnitude plot of the system, phase plot of the system is called frequency response. So magnitude plot means magnitude versus frequency, phase plot means phase versus frequency, right? Now we are going to see another important topic, distortionless transmission. This topic is very, very important. Distortionless transmission of the signal. Distortionless transmission of the signal through the linear system, through the linear system or LTI system, linear and time invariant system, through the linear system. So this is a topic, very, very important topic. Okay, distortionless transmission of the signal through the linear system. First of all, what is distortion? That we will discuss. Suppose this is the linear system. Consider this is a linear system. So the input signal is, this is the input signal. Suppose 0 to 2 seconds it is available. So distortion less means shape of the output signal. Okay, so x of t is the input signal, the amplitude is 3. For example, the output is also similar to input, exactly same as input, exactly same as input. Suppose 0 to 2, so the amplitude is here 5, so amplitude is increased, so this is the y of t. So if you observe the shape of the input signal and output signal, if you compare, so there is no shape change, output is exactly same as input. Okay, output is exactly same as input, then this is called distortionless transmission. This case is distortionless transmission because the output signal is exactly same as input signal, but here amplitude is increased by or increased to 5, so that is not considered as distortion. Increase in amplitude, constant increase in amplitude is not taken as distortion, right? So this is distortionless transmission. This case, distortionless transmission. Okay. For example, if the output is output signal shape not same as input, output signal shape is not same as input, that is called distortion. That is called distortion. Okay. So transmission of signal through system, we are transmitting the signal through system, and we can say distortionless if the output signal is exactly same as input signal. So that point I am writing here. So distortionless transmission means, what is the meaning of distortionless transmission? Distortionless transmission or distortionless. If output signal is exact replica of an input signal, same as input signal, then that is called distortionless transmission. That is called distortionless transmission. Otherwise, if output signal is not exactly same as input, that is called distortion. That is called distortion. So now the system has to satisfy, this has to satisfy two conditions to get the distortionless output. It has to satisfy two conditions for what? Distortionless transmission. Okay. So that distortionless transmission conditions we are going to see now. So let's consider the figure again, the same as above. So let's take the input signal x of t and system. Okay. So this is the system, and input signal is x of t, output signal is y of t. Okay. So consider input is, it is available from 0 to, the signal is available from 0 to capital T. So the amplitude of the input signal is, for example 1. This is the x of t, input signal. Now the output signal is, let's consider output is like distortionless output. So output must be same as input. The output signal shape must be same as input signal. Distortionless transmission we are discussing about, that is why. But the output is started from TD instead of 0. Input is started from 0, but the output is started from TD. Sometime late the output is coming, and the amplitude also increased to value k. The amplitude is k. So this point is TD starting, output starts from TD. After TD time the output is coming, and this point will become, what this point will become? TD plus capital T, but because the input signal is available from 0 to capital T. So output is delayed. What this delay 0 to TD, that is called delayed. Output is late or delay by TD time or TD amount. And here amplitude of the output signal is increased to k. It is changes to k, but shape of the signal is same, exactly same as input. So this is distortionless. So here 2 points I want to mention. One point is constant change in amplitude, constant change in amplitude, constant change in amplitude, and delay, constant change in amplitude, and delay in output, delay or time shift. We can call time shift because the output signal is shifted to TD seconds. So delay or time shift. So these two are not considered as distortion. Not considered as distortion. They are not taken as distortion. Distortion means only shape of the signal is different with respect to input, that is called distortion. So amplitude is increased or decreased, output coming late. So these are not considered as distortion. Okay, not considered as distortion. So we go by these points. Now mathematically we can express output signal mathematically. The output y of t is equal to, we can write the relation output and input mathematically. So they are looking same, they are similar, okay, or they are replica, same. So that is why x of t, and the output is started from TD, so shifted to TD, right shift, that is why x of t minus TD, and amplitude is k, so k into x of t minus TD. So this is the output signal y of t, right or not? So we are going to see conditions for distortionless transmission. That is why I have considered the figure distortionless transmission. So mathematically this is the relation y of t equal to k into x of t minus TD. Then we are going to apply Fourier transform on both sides. Apply Fourier transform on both sides. Let's take this step. For Fourier transform of y of t is equal to Fourier transform of k into x of t minus TD, right? So y of t Fourier transform is y of omega. So here k is a constant, we can write outside. X of t minus TD, we know time shifting property. X of t Fourier transform x of omega, then Fourier transform of x of t minus t naught. It will become x of omega into e to the power minus j omega t naught, time shifting property. So this property here we can use because here also we have time shifting or time delay. So x of omega into e to the power minus j omega td, e to the power minus j omega td. Now if you take the magnitude, or you can write transfer function y of omega by x of omega is equal to h of omega, which is transfer function k into e to the power minus j omega td. So here h of omega is the transfer function of the system. Just before we discussed transfer function of the system, output input Fourier transform ratio, transfer function of the system, right? And this transfer function is like r into e power j theta, right or not, in polar form. So what is r called? Magnitude. So here the magnitude h of omega is equal to how much? K, which is a constant, right? Magnitude is constant and independent of frequency. There is no omega term in k. K is a constant. So this point also please note, independent of frequency. Independent of frequency. So magnitude will not change with respect to frequency. It is constant always for all frequencies. And phase if you see phase, phase means angle of h of omega, that means theta. So in the place of theta, what we have? Minus omega td. So it is depending on frequency, okay, and it is linear relation. The phase is linear with the frequency. As the frequency increases, phase also changes, decreases, phase also changes, okay, linear relationship. So phase is linear, magnitude is constant. The system magnitude is constant, magnitude plot is constant, and the phase plot of the system is linear. Then that system will give you distortionless output. That system will provide distortionless output. So these two conditions, the first condition, magnitude response, phase response. So magnitude must be constant, phase must be linear. Then the system is said to be distortionless transmission. The system gives distortionless output if these two are satisfied. These two conditions are okay, then the system gives distortionless output. Distortionless output. Okay, so these two are the conditions. The same two conditions we are going to plot. So first one, the magnitude is constant, magnitude plot. So what is the constant? K. So draw the line K, amplitude K. So this is the magnitude plot, magnitude of h of omega. Okay, this is magnitude plot. And second one, phase plot. So phase is linear. So this is omega and this is the phase, angle of h of omega. So what is the phase we have? Minus omega td, right? Okay, for positive frequency, negative phase you get. For negative frequency, positive phase we get. So the graph is like this. This is a graph. Okay, so as omega is positive, we get negative. As omega is negative, we get positive phase, but linear because of this relation. So phase is linear, the system phase is linear, and magnitude is constant. Magnitude is constant, right? So these two conditions are must to give distortionless output. These two are 1 and 2 are must to give distortionless output. Distortionless output. So this is the distortionless transmission. So very simple, right? The magnitude plot of the system is constant, phase plot is linear. That's all. Another topic we are going to discuss, causality and Pauli-Wiener criteria. Pauli-Wiener criteria for physical realization. Pauli-Wiener criteria for physical realization. For physical realization of the system, physical construction or realization of the system, realization of the system. So first we discuss causality. What is meant by causal system or causality? So causality means, this point already we discussed. A system is said to be causal if its impulse response h of t is 0 for t less than 0. So this is the condition, simple condition, h of t value 0 for t less than 0. Then the system will become causal system. Now polynomial criteria for physical realization. What is physical realization? A system is said to be causal if its impulse response is 0 for t less than 0. Physical realization means physically possible to construct the system in real time. Physically possible. So physical realization means physically possible to construct the system in real time. So practically we can design the system or we can construct the system, that is physical realization. Okay, physically possible to construct the system in real time, that is the physical realization. Okay, for physical realization we have criteria, that is polynomial criteria. To construct the system practically or in real time, that has to follow polynomial criteria. Okay, so in frequency domain, integral minus infinite plus infinite log h of omega by 1 plus omega square d omega. This integral value, log h of omega by 1 plus omega square d omega, this integral value is less than infinity, such that integral minus infinite plus infinite magnitude of h of omega square d omega is less than infinity. So what is magnitude of h of omega square and integration? Area, integration is the area. So area under magnitude of h of omega square is less than infinity, means what? Finite. So this is the condition in frequency domain. So just again we discuss, causality means the system impulse response h of t is 0 for t less than 0. Simply causal systems means the output is 0 before input is connected or input is applied. They start producing output whenever the input is connected. If input is connected, output is present or output starts coming. If input is not connected to the system, output also not there. Such character is causality. Okay, so the same point in frequency domain, that is polynomial criteria in frequency domain. So integral minus infinite plus infinite log mod h omega by 1 plus omega square d omega value is less than infinity, means finite. And this one also, integral minus infinite plus infinite mod h omega whole square d omega is less than infinity. So here integration is area under magnitude of h of omega whole square is finite. So this is the condition or criteria in frequency domain. This criteria is polylinear criteria. This criteria, this one and this one, these two are polylinear criteria. So this criteria is in frequency domain. This is in frequency domain. In time domain, h of t is 0 for t less than 0. And physical realization means if you are able to design the system practically, possible to design the system practically, that is called physical realization. Right? So thank you students. Thank you. Please watch videos regularly. Thank you all.